Download this code from codegive.com, link in the description below. Building and scaling a control plane for thousands of Kafka clusters. Managing a vast number of Kafka clusters, 1000 plus, requires a robust and scalable control plane. This tutorial outlines the key considerations, architectures, technologies, and code examples needed to build such a system. The challenge: why a control plane? Scaling Kafka infrastructure beyond a handful of clusters presents significant challenges. Complexity, manual management of configurations, deployments, upgrades, and monitoring becomes unsustainable. Consistency, ensuring consistent configurations and security policies across all clusters is difficult. Observability, gaining a holistic view of the overall Kafka ecosystem becomes near impossible. Automation, lack of automation hinders rapid deployment and incident response. Security, implementing and enforcing consistent security policies across the board is complex and error-prone. Resource optimization, efficient resource allocation and utilization become difficult. A control plane addresses these challenges by providing a centralized system for managing the entire Kafka ecosystem. 2. Core components of a Kafka control plane. A robust control plane typically comprises the following core components. 1. API gateway / ingress * exposes the control plane functionalities to users, administrators, developers, and external systems through well-defined APIs. 2. Authentication and authorization * secures access to the control plane, ensuring only authorized users can perform specific actions on specific clusters. 3. Cluster registry / inventory * maintains a comprehensive record of all Kafka clusters, including their metadata, name, region, version, configuration, broker details, zookeeper / craft information, connectivity details, health status, etc. 4. Configuration management * stores and manages configuration templates and overrides for different cluster types and environments. Enables consistent and automated configuration application. 5. Deployment automation * automates the provisioning, scaling, and decommissioning of Kafka clusters. Integrates with infrastructure as code, IAC, tools. 6. Monitoring and alerting * collects metrics from all Kafka clusters and provides centralized monitoring dashboards and alerting capabilities. 7. Security policy management * defines and enforces security policies, example ACLS, TLS/SSL configuration, data encryption, across all clusters. 8. Audit logging * records all actions performed within the control plane for auditing and compliance purposes. 9. Self-healing / automated recovery * detects and automatically recovers from failures, such as broker failures or zookeeper / craft issues. 10. Upgrade management * simplifies and automates the upgrade process across all Kafka clusters. 3. Architectural considerations. Microservices architecture * decompose the control plane into independent microservices for improved scalability, fault tolerance, and maintainability. Each component, example configuration management, deployment automation, can be deployed and scaled independently. Stateless services prefer stateless services whenever possible to simplify scaling and reduce the impact of failures. State can be stored in a centralized database or distributed key-value store. Asynchronous communication use asynchronous communication, example message queues like Kafka itself, RabbitMQ, or cloud-native queues, for internal communication between microservices. This improves responsiveness and decoupling. Event-driven architecture * design the system to react to events, example cluster creation, broker failure, configuration change, and trigger appropriate actions. Idempotency ensure that operations are idempotent, meaning that executing the same operation multiple times has the same effect as executing it once. This is crucial for handling failures and retries. Data consistency choose an appropriate data consistency model based on the specific requirements of each component. Consider eventual consistency for less critical data and strong consistency for critical data like cluster configurations. Infrastructure as code, IAC use IAC tools, example Terraform, Ansible, CloudFormation, to define and manage the underlying infrastructure for the control plane and the Kafka clusters. Containerization, Docker containerize all components of the control plane and the Kafka brokers for consistent deployments and portability. Orchestration, Kubernetes use Kubernetes or a similar container orchestration platform to manage the deployment, scaling, and self-healing of the control plane components and the Kafka brokers. 4. Technology stack. A possible technology stack for building a Kafka control plane. Programming languages Go, Python, Java, Kotlin, Node.js. Frameworks Spring Boot, Java, Flask/Django, Python, Gin/Echo, Go, Express.js, Node.js. API Gateway Kong, Traffic, Ambassador. Authentication/authorization OAuth 2.0, OpenID Connect, Keycloak, Auth0. Database PostgreSQL, MySQL, MongoDB, Cassandra. Distributed Key Value Store *ECT, Consul, Zookeeper, for internal use, Redis. Message queue Kafka, RabbitMQ, AWS SQS, Google Cloud Pub/Sub, Azure Service Bus. Monitoring Prometheus, Grafana, Datadog, New Relic. Logging Elk Stack, Elasticsearch, Logstash, Kibana, Splunk. Infrastructure as code Terraform, Ansible, CloudFormation. Containerization Docker. Orchestration Kubernetes. vCode examples, illustrative. This section provides illustrative code examples using Python and Flask. The complete implementation would involve more complex logic and integration with other components. 1. Flask API for cluster registry, Python. Explanation This code creates a Flask API for managing a cluster registry. The create_cluster endpoint creates a new cluster entry and initiates a deployment task, placeholder for asynchronous task execution. Crucially, it captures the Kafka_version. The get_cluster endpoint retrieves cluster information by ID. The update_cluster endpoint allows updating cluster attributes, example status. The list_clusters endpoint returns all clusters in the registry. The in-memory clusters dictionary should be replaced with a persistent database like PostgreSQL or MySQL in a real implementation. 2. Configuration management, simplified, Python. Explanation This code demonstrates a simplified configuration management function. It loads configurations from YAML files based on cluster type and environment. Crucially, it factors in the Kafka version, allowing you to maintain separate configurations for different Kafka versions. The load_Kafka_configuration function takes the cluster type, Kafka_version, and environment as input. It first loads a base Kafka configuration from a versioned file, Kafka_base_3.4.0.yaml. Then, it merges type-specific and environment-specific configurations on top of the base configuration. Error handling is included to gracefully handle missing configuration files. The YAML.dump function is used to print the loaded configuration in a human-readable format. Example configuration files, YAML. config/kafka_base_3.4.0.yaml, base configuration for Kafka 3.4.0. config/analytics.yaml, type-specific configuration for analytics clusters. config/production.yaml, environment-specific configuration for production. 3. Deployment automation, illustrative, using Terraform, example Terraform configuration. This example shows a simplified Terraform configuration to create a single Kafka broker instance. In a real-world scenario, you would need to create a more complex configuration with multiple brokers, zookeeper/craft, networking, and security. Explanation ***This Terraform configuration defines an AWS EC2 instance that will host a Kafka broker. It uses the AWS_instance resource to create the instance and configures it with a startup script using the user_data property. The user_data script installs Java, downloads and extracts Kafka, configures Kafka, and starts the Kafka server. You would parameterize the Kafka version in a real-world scenario. It also defines a security group to allow traffic to the Kafka broker. Important the security group allows traffic from anywhere, which is not secure for production environments. You should restrict the traffic to only the necessary sources. This is a very basic example, and you would need to adapt it to your specific requirements. You would typically use variables to parameterize the configuration and modules to organize the code. 6. Scaling the control plane. Horizontal scaling. Scale the control plane components horizontally by adding more instances of each microservice. Kubernetes makes this easy to manage. Database sharding. If the database becomes a bottleneck, consider sharding the database to distribute the load across multiple servers. Caching. Use caching to reduce the load on the database and improve response times. Redis or MEMC are good choices. Load balancing. Use a load balancer to distribute traffic across the control plane instances. Resource limits. Set appropriate resource limits, CPU, memory, for each microservice to prevent resource exhaustion. Monitoring and alerting. Continuously monitor the performance of the control plane and set up alerts to notify you of any issues. Prometheus and Grafana are excellent choices. 7. Security considerations. Authentication and authorization. Implements strong authentication and authorization mechanisms to control access to the control plane and the Kafka clusters. Encryption. Encrypt sensitive data at rest and in transit. Use TLS/SSL for communication between the control plane and the Kafka clusters. Network segmentation. Segment the network to isolate the control plane and the Kafka clusters from other parts of the infrastructure. Regular security audits. Conduct regular security audits to identify and address potential vulnerabilities. Least privilege. Grant users only the minimum privileges necessary to perform their tasks. Secrets management. Use a secure secrets management system, example HashiCorp Vault, AWS Secrets Manager, to store sensitive information such as passwords and API keys. 8. Deployment strategy. *blue/green deployments. Use blue/green deployments to minimize downtime during deployments. *canary deployments. Use canary deployments to test new versions of the control plane components in production before rolling them out to all users. *rolling updates. Use rolling updates to gradually update the control plane components without interrupting service. Kubernetes provides built-in support for rolling updates. 9. Monitoring and observability. *metrics collection. Collect metrics from all control plane components and Kafka clusters. Prometheus is a popular choice for metrics collection. *centralized logging. Centralize logs from all control plane components and Kafka clusters. The ELK stack, Elasticsearch, Logstash, Kibana, is a common choice for centralized logging. *tracing. Use distributed tracing to track requests as they flow through the control plane and the Kafka clusters. Jaeger and Zipkin are popular tracing tools. *dashboards. Create dashboards to visualize the performance of the control plane and the Kafka clusters. Grafana is a popular choice for creating dashboards. *alerting. Set up alerts to notify you of any issues. Best practices. Automate everything. Automate all aspects of the control plane, from deployment to monitoring. Infrastructure as code. Use infrastructure as code, IAC, to manage the infrastructure for the control plane and the Kafka clusters. Treat infrastructure as immutable. Avoid making manual changes to the infrastructure. Instead, use IAC to define the desired state and apply changes automatically. Embrace DevOps principles. Foster a culture of collaboration between development and operations teams. Continuous integration and continuous delivery. CI/CD. Implement a CI/CD pipeline to automate the build, test, and deployment process. Version control. Use version control, example Git, to track all changes to the control plane code and configurations. Document everything. Document all aspects of the control plane, from the architecture to the deployment process. 11. Real-world considerations. Cloud provider vs. On-premise. The choice of cloud provider, AWS, Azure, GCP, or on-premise deployment will influence the specific technologies and services used. Cloud providers offer managed services that can simplify the implementation. Kafka distribution. Consider the Kafka distribution you are using, example Apache Kafka, Confluent Platform, Cloudera. Different distributions may have different requirements and capabilities. Existing infrastructure. Integrate the control plane with existing infrastructure and tooling. Team expertise. Choose technologies that your team is familiar with or can quickly learn. Cost optimization. Optimize the cost of the control plane by using appropriate instance sizes, storage options, and networking configurations. Vendor solutions. Explore commercial control plane solutions that may offer pre-built functionality and simplify the implementation. Examples include Confluent Control Center, Lenses.io, and others. 12. Conclusion. Building a control plane for thousands of Kafka clusters is a complex undertaking that requires careful planning and execution. By following the principles and guidelines outlined in this tutorial, you can build a robust, scalable, and secure control plane that simplifies the management of your Kafka infrastructure. Remember to prioritize automation, monitoring, and security throughout the entire process. The illustrative code examples provide a starting point for building your own custom control plane. Remember to tailor the architecture and technology stack to your specific needs and constraints. Good luck.